Okay? Plus 5 oxygen atoms times its oxidation state. Oxygen will be -2 when we go through to solve these. The overall charge for that first molecule, how do you know it's 0? Look at the upper right-hand corner of that molecule and you see nothing written there. So we're looking at a zero charge. We then go through and solve for X, and we determine that the oxidation state on the iodine is a +5. Okay? We could then go through and do that with the rest of the atoms within this. And hopefully, given enough time, or hopefully you've already done it, you should be able to determine the oxidation states for each of the atoms, both on the reactant side and the product side. So when we go through and look at the reactants, our iodine molecule is +5. Each oxygen atom is a -2, and our carbon is a +2. On the product side, take a look at the iodine, I2. Why is it 0? Does it make sense for it to be 0? Iodine, or anything in its elemental state, has what charge? 0. I2, why is that its elemental state? Iodine is one of the diatomic elements. Okay, so we expect I2 out of that. Okay, so if we take a look at iodine across the reaction, we went from a +5 to a 0. How could we possibly do that? How do we change the charge from +5 to 0? We have to do some kind of charge transfer. What's the easiest way to transfer charge? What are our charged particles? There's 2 of them. Electrons and protons. Why do we not change the protons? Why do we not transfer protons in an individual electron, or sorry, not electron transfer, or redox reaction? What's that? The protons determine the element. If we change the number of protons, it's no longer the same element. Okay? However, if we change the number of electrons, it's still the same element. Okay? It just changes its oxidation state. So our electron count is really what's changing and determining our oxidation states. Okay? So if we try and move from reactants to products, as far as our iodine went, it had to gain electrons. Okay? How does that work? What charge is an electron? Negative. So what happens if we gain a negative? Become more closer to negative. So we move from a +5 to a +4 to a +3 to a +2, +1, and 0. So what we've done is reduced the charge. Okay? We've become more and more negative. What happened to the oxygen? Started -2, ended -2. So nothing changed. Its oxidation state was consistent between it. How about the carbon? Moved from a +2 to a +4. Okay? To become more positive, what does it need to have lost? Electrons. We could look at it saying, oh, but it adds positive, so it has to be a proton. What happens if we add a proton? It's not carbon anymore. So the only thing we can shift around are the electrons. So to go from a +2 to a +4, we had to remove negative charge from it. That's where we lose our electrons. Okay? Why does this get easy to confuse? We're adding and subtracting negatives. Okay? So the sign in this material is just as painful to watch out for as it is in the previous material. Okay? It's relatively easy. But it's just as much as it's relatively easy, it's also easy to get it confused and start changing your signs the wrong direction. Okay? So make sure you're careful when you go through and apply those. Okay? Instead of looking at gain of electrons and loss of electrons, someone went through and decided to change the terms around or come up with better ways to refer to them. And that's where we get a loss of electrons is oxidation, and a gain of electrons is reduction, which hopefully you already remember. Okay? The mnemonic device that I like to use is Leo says GER, but there are other ones out there. I think I've got another one up here. Oxidation is loss of electrons. Reduction is gain, or oil rig. Both of those are equally valid. It just comes down to whichever way you want to remember that relationship. Okay? Questions about that? Okay. One more thing I want to review. We could go through and look at what was reduced and what was oxidized, and we just apply those definitions that we already had. So if something lost electrons, it was oxidized. If something gained electrons, it was reduced. Nice and simple. Okay? But what ends up happening is we add this other idea into it, and instead of looking at oxidized and reduced, we look at oxidizing agents and reducing agents. Okay? So when we say oxidizing agent, most people tend to think, oh, oxidized, because it says oxidized in the name. It must be oxidized. No, what does an oxidizing agent do? Causes something else to be oxidized, which means what happened to it? It had to be reduced. Okay? So make sure you're careful when you're applying those definitions. If we ask for the thing that was oxidized, that's fairly straightforward. Okay? It's the thing that lost electrons. If we asked for the reducing agent, what do we need to look for? The species that was oxidized or the species that lost electrons. Okay? So be careful with how you apply the definitions. That ing can mess with a lot of how you solve problems. The other way you might see it is oxidant or reductant. Okay, so ing and ant are both implying the same kind of thing. Okay? Hopefully it's all review, right? Yes? Okay, a few yeses, that works. So we could go through, oh man, I don't want to deal with more oxidation states. We could go through and identify more oxidation states. You guys definitely seem a little bit bored, so let's speed this up. You could go through and apply all of your definitions, go through and determine the individual oxidation states. For that first one, it's a bit simple because the charge shown is the oxidation state for each of those quote-unquote molecules. Okay? We could go through and look at how things changed as we move from reactant to product. Okay? And we could say what things were oxidized, what things were reduced. We could then go through and do the next one. That's a little bit more tricky because we actually have full-on molecules. We actually have to calculate our oxidation states. We can get the same idea, looking for how those electrons were transferred across the reaction, determine what was oxidized, what was reduced, and apply those. Why did oxygen not show up as one of the things oxidized or reduced in the second one? Because oxygen's oxidation state stayed the same. All right. Last one is even more obnoxiously long. All sorts of different atoms to apply in there. You'll notice there's a lot of spectators that didn't actually change their oxidation states. The more complex the problems get, typically, the more spectator ions get thrown in there, or spectator atoms that don't change their oxidation states. So make sure you're careful when you go through and apply. And make sure you apply those definitions carefully. Okay? Questions? Okay, is it because it's Monday and you're tired, or is this just that easy? This is easy, okay. So, we'll definitely be able to get through this. Balancing redox reactions. Okay? In some cases, it's trivial. So if we were trying to balance the case of hydrogen ion reacting with zinc, we could go through and look at that redox reaction and evaluate that we don't have the correct number of atoms to balance across the reaction, and all we end up doing is sliding that 2 in front of the H+, and now everything's balanced, everybody's happy, and there we go. Okay? But other times, it may appear trivial, but it's not. Okay? For instance, if we take a look at this next one, how many tin atoms do you see on the reactant side? Tin, by the way, is SN, just in case. See, 1. How about on the product side? 1. Hey, tin's balanced. How about iron? 1 and 1. Hey, iron's balanced. However, this reaction isn't balanced. Okay? When we go to balance reactions, in 151 you just looked at the atoms. Okay? In 152 we're going to make it a little bit more difficult, and what we've got to do is account for charges or oxidation states, or electrons. Okay? So if we look at the charge on the reactant side of this equation, what is the charge? Plus 5. How do you know it's plus 5? You just added those two atoms up. Iron, or tin plus 2 and iron plus 3 gives us a total of plus 5 for our charge on the reactant side. What about the product side? Plus 6. Is the charge balanced? No. Okay, but wait, we've already seen how to fix this. We just need to make sure we add enough electrons in here. So what we could do is we need to make sure those charges equal each other, so let's just add an electron to the appropriate side of the equation. Where should we put that electron? Reactant or product? Why the product? Plus 6 plus a negative gives us plus 5. Now our charges is balanced. Is balanced? Charges are balanced. Great, that's fantastic. Yeah, our charge looks balanced. There's one big issue with this though. How stable are electrons? Freakishly unstable. Okay? They cannot transport themselves outside of an atomic structure. They must stay within the atomic cloud, which can mean they can shift from an atom to, say, a bond, but they can't jump from atom to atom. So that gives us a problem here. In this course of this reaction, we're saying there's an electron that is freely floating around, not attached to anything. That is not physically possible, as far as we're concerned. Okay? So that means our equation's not balanced. We have to go through and treat this in a different situation. Okay? We have to account for our overall reaction having no electron counts. Our charges must balance. Okay? So what we're going to do is look at one method for this. We're going to split this reaction up. We know there's two portions to it because our charges ultimately have changed. We have to do some transfer of electrons, which means we're doing redox. So one reaction or one reagent will reduce, one reagent will oxidize. So what we'll do is split our reaction into the individual partners. We could look at our reduction and our oxidation. Okay? So we'll pick essentially our conjugates, if you will, across that reaction. When we take a look at the iron, we're going from iron plus 3 to iron plus 2. Okay? That charge is not balanced. What do we need to do? We need to add an electron to stabilize it. How do we do that? The electron's going to go on the reactant side. Let's see, did I stepwise this? Hey, cool, look at that. And we could go through and do the same thing with our oxidation, with our tin, and we'd see the electron added to our product side. Okay? If we were now to add these two equations up, we would get the exact equation that we just had, an electron left over. We cannot have an electron left over, which means that that electron, as it's produced, must be consumed by something else. The only place where that electron's getting consumed is in our reduction reaction. We must, well, let's see, do I double everything? Nope, I didn't. Oh, I really stepwise through this. We must multiply that top equation by 2. Okay? When we go through and multiply that by 2, the coefficients change all the way through that. Did I do that? Yeah, I did. Wow. Okay? Now when we add the two equations together, we'll notice that the electron count balances out, and we don't have to worry about our electrons in our overall reaction. So now when we look at our final result, you'll notice the coefficients aren't all 1. Okay? We had to account for that charge. By splitting it into the half reactions, we were able to account for that charge a little bit easier than we were before. Okay? Forget, you learned that in 151? Seeing some no's. Okay? So what we want to do is, again, split our reactions into those individual species, or into the individual half reactions, both our reduction and oxidation. Balance those first, then evaluate our charge. And if we end up with excess electrons or excess electrons consumed, we'll have to multiply the half reactions by some whole number so that when we do add the reactions up, the electrons cancel. Okay? So one easy way to check and verify that this was done properly, what's the charge on the reactant side? Oh, wow, I didn't do that math very well. Okay, we've got +3 times 2, so we've got 6 from that plus another 2 plus 8. What's the charge on our product side? Is our charge balanced? Yeah. Okay. So one quick, nice way that we can verify that our work was correct is we can go through and again check to make sure that the atom count on both sides of the equation come out the same, just like you did in 151. But now also evaluate charge. Is the charge the same on both sides of the equation? Okay? As long as the charge is the same, everything's good, you balanced it appropriately. Okay? Questions about that one? I could have sworn you guys had this before. Okay, because it only gets more difficult. Okay? We could go through and look at another one. If we split this one into the half reactions, what happens? Do we get an electron balancing? No. So what do we have to do? We're going to have to multiply the reduction by 2, so we change our coefficients. Now when we add the two equations up, our electrons cancel. We get our copper solid plus 2 nitrate ions. We'll go to our copper ion and our 2 NO2. Okay? Oh, did that work? No. Why not? So we could look at our charges. -2, +2, that didn't work. What else is wrong with it? Oxygen's not balanced. Okay? So sometimes when we go through and balance the equation, it may appear that we could go through and do that new little trick. We split it into half reactions, make sure our electrons balance out. Except before we even get into the electrons, we have to make sure our atoms balance out. And in this case, did our atoms balance out? No. So don't skip steps. We need to go back and evaluate. Our copper sure is fine, but then what happens when we get to our reduction? Nitrogen looks fine, balanced on both sides, but our oxygen is not. How would we balance the oxygen? Okay, and that's where this material gets even more tricky. What we're going to end up doing is adding water. Okay? What's the problem with adding water? Yes, that balances our oxygen, but then what does it contribute? It also contributes hydrogen. So now we add water to fix our oxygen problem, but now we have a hydrogen problem that we also have to fix. How do we fix our hydrogen problem? We'll add hydrogen ions, okay, or our acid. Okay? So I don't think I want to do this one quite yet because I want to go through the steps. Okay? So if we take a look at our reduction reaction, we're now going to break it into our individual steps on how we apply. So instead of immediately jumping to our electrons, we want to slow it down. Our first step is going to be to make sure we balance everything in that half reaction. Again, we still want to be in half reactions, except for our oxygen and our hydrogen. Okay, in this case, we would go through and look at our nitrogens. Nitrogen on both sides is the same. We don't have to worry about it. Next step is to balance either any other elements, which we don't have, or go through and balance our oxygens. To balance the oxygens, we will add water to the appropriate side of the equation. Okay, sorry this didn't step as nicely as I would have liked. If we compare across our reaction, we had 3 oxygens here, 2 oxygens here. To fix that, we need an extra oxygen atom on the product side. To do that, we'll just add 1 molecule of water. Now when we total up the oxygen atoms on our reactant and product sides, they both come out to 3. We're nicely balanced. Okay? Next part of it is adding our hydrogens. So if we look across the reaction now, our nitrogens are balanced, our oxygens are balanced, but now our hydrogens aren't. Okay? One of the advantages of adding water is water can also contribute H+. That can dissociate potentially to give us our H+ ion. So because we can take advantage of the acidic environment really, really readily, or in acidic chemistry really easily, we will go through and balance the hydrogen now with hydrogen ions. What's the nice thing with balancing with hydrogen ions? We don't add any other atoms. Okay? It's just hydrogen, which means we can now say our total is balanced. So in this case, because we brought in one water molecule, we see two hydrogen atoms show up. So what we'll do is add two hydrogen ions to balance that out. Now we can go through and balance our charge, okay, with our electron count. So there's two ways to approach this, is balancing the charge on the totals on both sides of the reaction. When we go through and look at it, what's the charge on our reactant side? What is it? +1. Why +1? What happens on our product side? So now to get +1 equal to 0, what do we need to add? We need to add one electron to balance out that plus charge, and now we're overall balanced. So we can use the electrons and our charge states, or our charges, to balance out our electron count. The other method, which depends on who you are and how much practice you've had with either of these two methods, which one you'd prefer, we could look at the element that's losing or gaining electrons. In this case, we're looking at a reduction. Which element was changed? Which element was reduced? Ammonia. Which element? Our nitrogen. What's the oxidation state on the nitrogen on our reactant side? See how many of you can do that in your head. Should come out to be a +5. And then the product side comes out as a +4. How can we make sure our oxidation states balance? We need an extra electron on the reactant side. So when we're balancing with our electrons, we can look at charge or we can look at oxidation state. It is entirely up to you which one you want to go through and do. Most problems you have to figure out the oxidation states anyway, which would suggest that it actually makes sense to balance based on the oxidation state. But that is entirely up to you. Okay? You will get the exact same answer regardless of how you do it. At this point, we've now gone through with all those arrows and circles and lines. We've gone through and balanced just the half reaction. Okay? What we wanted to do was to balance the whole reaction. So what we would now have to do is translate that equation back over to our other process. Copper released 2 electrons, which means our nitrogen must accept 2 electrons. So to do that, I have to multiply the reduction reaction by 2 all the way through it. See, did I do that? Yep, I did. And then we can add our 2 expressions together to get one overall completely balanced, charge balanced, atoms balanced, everything's perfect equation. Okay? Depending on how difficult the problem was or how many different extra steps you had to go through, you might be able to cancel like terms. The like terms that we would be canceling other than electrons would be water or H+. Okay? Questions about that? Okay, please say... Okay, balancing everything all the way through. Split into your individual half reactions. Get your oxidized reaction and your reduction reaction set up. Okay, balance each half reaction. Go through, balance all elements other than oxygen and hydrogen. In most cases, you only have to balance one. And then balance your oxygen with water. Balance your hydrogen by adding H+. Then you can balance your charge or your oxidation states by adding electrons to the appropriate side of the equation. Now that you've got your half reactions balanced, you can then add the two half reactions back up, assuming your electrons cancel. If the electrons don't cancel, multiply by the appropriate whole number integer to get the electrons to cancel out. Then add your equations, and then check. So after all of this work, one of the nice things about these balancing reactions, at the end of it, you know you got the question right, or you know you got the answer wrong. Every single time. Okay? No exceptions on that. Since I got time, let's go through and work one more together. And then tomorrow we'll probably start with a quiz, which is looking at balancing, breaking it all into the individual steps, and looking at all the pieces. Okay? So if we were going to try and balance this, our first step is going to be the faster you give me steps, the faster we can get through it and leave. Break it up into our half reactions. Which half reaction do you want to look at first? I agree. Iodide goes to, what's its conjugate? It's the thing that looks most like it on the product side. Okay. Is that balanced? No. So the first thing to do with that one, balance the atoms other than oxygen and hydrogen. How do we do that? Put a 2 there. Now our atoms are balanced. We don't have any oxygens or hydrogens to worry about, so we can now go through and evaluate charge. What's our charge on the reactant side? -2, because there's 2 iodide atoms. Our charge on the product side? 0. What has to happen to get those charges to balance? We need to add electrons somewhere. Where do we add them?
Product side.
Product side. Just in case you all are guessing, let's say we guess the other side. What happens? Becomes more negative. Okay? So when you add it on, just check your work real quickly. Remember, you're adding a negative charge. It can be very easy to get that messed up, so add it carefully. If we just add 1 electron as our charge balance, what do we need to do? 2 electrons. We now have our balanced charge. We now have the half reaction. What occurred to our iodide atom? Is it oxidized, reduced? Electrons are on the product side, which means it lost electrons, so it was oxidized. What happens with our other half reaction? Balance atoms other than oxygen or hydrogen. So we've got our nitrogens. Are those balanced? Yes. So now what do we do? Now we can balance our oxygen. Is the oxygen balanced? No. What do we need to do? Add water to our product side so that our oxygen now balances out. What's the problem? Now we've got too many hydrogens on the product side, so we have to add hydrogen atoms to our reactant side. How many hydrogen atoms do we need? 2 hydrogen atoms. Okay, now what? Now we can balance our charge. What's the charge on the reactant side? Charge on the product side. How do we make them equal to each other? We need to add an electron where? On our reactant side, need a little more space there. Now our charge balances out. So now what do we do? Now we could try and go through and add them, but before we add, we have to make sure the electron count's the same. Is the electron count the same? Nope, so what do? We'll multiply our bottom equation by 2. 2 times 1 is 2. 2 times 2 is 4. Good. 2. 2, 2. Now we can add our equation up. The electrons are on opposites. Whoop, there we go. That's going to be the end of it. The electrons are on opposite sides, and we get our balanced overall reaction. Where we will pick up tomorrow is with the quiz. I'll probably go through and balance one more. I'll balance that second one. We'll start off kind of slowly with that. You guys can ask questions about balancing, particularly in reference to the second one. The quiz goes through and has you balance the third one. Okay? So if you want to get a jump start on balancing that, feel free to go ahead and do so. And